Okay, so thus far we've talked about capturing data, whether it's about the program or intervention or outcomes. Now, for the rest of the day, we're going to think about how to use that data in an impact evaluation causal inference design. Of course, our goal is to capture an accurate counterfactual. We've got a bunch of options: experimental designs, quasi-experimental designs to deal with this. In experimental versions, we're going to rely on the randomization to create the groups whose expected outcomes are similar. These cases are going to give us direct control over the design, but that also means we can only really do them prospectively. The main thing I want to say about experimental designs today is that the remote sensing aspect of what we're talking about can dramatically improve the spatial coverage by giving us larger and denser samples, and the temporal coverage, including more frequent observations, but also longer tails, so letting us capture longer term outcomes from RCTs. I think these are particularly important because when we're dealing with RCTs, budget for data collection is almost always the constraining factor, and ends up being the driver for a lot of fundraising efforts and a lot of points of negotiation throughout. And remote sensing can ease those budget constraints in important ways. Again, the improved spatial coverage can give us additional opportunities for subgroup analysis that we might not be able to power with traditional samples for only surveys. They can also let us better understand spillovers and other mechanisms that are going to be driving the overall results. And in that sense, it can really improve the full narrative of our ability to kind of draw the full narrative of what's going on. Similarly, the temporal coverage, maybe we're bound to do only like a baseline and an end line, or maybe a smaller midline round where we can kind of tell, 1 year in what's going on, and we've got a 2-year end line, because that's when the grant ends, and we've just got to, get something done as quickly as we can, right? But many of the interventions we're looking at take far longer to study, far longer to materialize. And if we can build in the remote sensing aspect to it, we can continue to monitor outcomes for years later. And that's going to let us draw far more powerful conclusions, I think, for many of these studies. There's also lots of opportunities to go back to already completed randomized trials now with that remotely sensed data. If the underlying survey data were kind of strong enough to do a little bit of calibration and maybe even some training of that remotely sensed data. So lots of opportunities, I think, and potential benefits for experimental designs. For the most part, though, we're going to focus on quasi-experimental designs. And that's partly because these are much more feasible retrospectively, or in some cases, even prospectively, but again, with existing data. In these quasi-experimental designs, we're going to construct the comparison groups retrospectively. We don't have control over them. And so we can take one of two different approaches. This is kind of my classification. Lots of folks who can, I'm sure, have your own kind of classifications of these designs. The first approach will be to attempt to account for or control for the factors that vary across the groups that might also be correlated with the outcomes. That'll be our differences in panel models. We can also attempt to use matching to further account for these differences, and sometimes combine matching with the panel models. Alternatively, we could look for natural experiments. These are cases when there is some factor that appears to be as good as randomly assigned that determines program participation. So look for one or two particular reasons that in otherwise identical or similar individuals or units nonetheless had differences in program participation. We'll look at some discontinuities and instrumental variable approaches to tackling this. Turning more narrowly to differences in panel designs more generally, these have become much more popular, partly because the units of analysis that we now have at our disposal are much finer than we might have had previously. Again, this partly because of the availability of remotely sensed data, but otherwise just the availability of much more finely georeferenced survey data or other outcome measures as well. That variation of treatment at finer spatial levels dramatically improves our statistical power. It's important to note, though, that what we're doing is making comparisons only between nearby or similar units, like all units within a district or even a village, even multiple plots for an individual household. And that when we're doing that, we're improving the reliability or the validity of causal inference by controlling for all these other confounding factors that vary across the larger units. It does have a cost. We are making comparisons that are narrower in scope. And so in that sense, we want to be more careful when we're aggregating those up to representative estimates of policy interventions at larger scales. But it is also powerful in combination with the fuller time series that we have at our disposal. Again, especially from remotely sensed data, we can control for the time invariant characteristics of even the finer units and use fixed effects at the unit level as well. That's, again, super powerful. In some cases, we can combine that with controlling for trends at more aggregate levels as well, because we've got enough of a time series that we're looking at variation really year to year or season to season. So these are increasingly common. Later on today, we're also going to look at some of the more recent literature on the two-way fixed effects models and what we're learning about what they when they might fail us, despite having used them now in hundreds, even thousands of applications in the last few years. Differences and differences we can think about under two main categorizations. One is where all units are treated simultaneously, and the second is where different units vary in their treatment timing. The first case, where all units are treated simultaneously, we're going to construct a comparison group of only untreated units in that case that remain untreated throughout the study period. And we're going to rely on controlling for time invariant factors that are correlated with the outcomes. Those might include aggregate fixed effects at district, again, or village scales, but other unit level covariates. With sufficiently long pre-trend time series, we're going to validate this by assessing any differences in the preceding pre-trends or changes. Important to note, again, we need long time series to do this. We can certainly do it with just one single difference beforehand, but those tests are often underpowered, as we're learning these days. And we can add matching to the comparisons, essentially to limit the comparison group from the much broader pool and make sure the comparison group on which we're actually running the analysis is the subsample that most resembles the treatment group in terms of the key variables. The second alternative, where we're using variation in treatment timing, is something that, again, we're doing much more of these days. It's quickly becoming the canonical approach. In this case, we're going to limit the sample to only the treated units. There are variations where you use the untreated units as well to contribute to estimating things like the time trends. But the comparison group here is going to consist of only not treated and not yet treated units. We're going to, or that's at least the goal. And again, we'll look at some two-way fixed effect models that really attempt to adhere to that more carefully. In this particular case, we can use both trends preceding the treatment as well as event study designs to assess the validity and make sure that there are no differential pre-trends in the run-up to the treatment window for any individual unit. So more broadly then, for geospatial impact evaluations, this is kind of one of our typical walkthroughs. So our first criteria that we think about, again, is the treatment timing. If all the treatments occurred simultaneously, we have a choice. We go to the second column where we think about the geographic distribution of the treatment. If the treatment is only in some areas based on unknown or known factors, we can turn to DID. Again, that's the first version of DID that we looked at just a moment ago, potentially combining it with matching and having never treated areas as the comparison group. If the geographic distribution in the second row also has boundaries that are well defined to it, like administrative boundaries, physical boundaries, etc., then we can leverage regression discontinuity to look at never treated areas, but adjust for the proximity to these boundaries that define the treatment more narrowly. And then in the third row, if the treatments in fact vary over time or multiple years or seasons, then we can leverage that variation over regions, making sure that they're varying within regions or administrative units to do GID with a staggered rollout. And again, in those cases, the goal is for the yet to be treated areas to be the comparison group. We're going to get into these in just a minute in a lot more detail.